All right, so welcome to lecture 2 of Introduction to Robotics. So today's theme is locomotion, and I'll talk a little bit more about the course roadmap in a couple of slides later, but for now, a couple administrative things. So one, your lab groups have been set and they are viewable on Canvas. If you have any like changes that you need to make for any reason, please post it on Piazza, send either a private message to the TAs and myself, or send an email to all three of us, just so that we can get that sorted as soon as possible, because tomorrow's lab is a group lab. Other things worth noting is that homework 0, the warm-up that covers a little bit of linear algebra and some introduction to Python stuff and path planning algorithms, is due this Friday at 5 o'clock. And so in general, with this class, if an assignment is due on any weekday that other than Friday, it will be due at 11:59 p.m. If it is due on Friday, it will be due at 5 p.m. because you probably shouldn't be working on intro robotics stuff between 5 p.m. and the rest of the weekend if you can avoid it. So that is why that date is going to be a little bit different. As I mentioned, Lab 1 continues this week. So the first week, Lab 1 was running through the tutorials, the first 4 tutorials in Weebots, just so you can get familiar with the simulation environment that we're going to be using. And so this week, you're going to be implementing a particular behavior on the robot, and you're going to do that as a group, and then turn that in next Tuesday. And that will be due at 11:59 p.m. So in the chat, quick question, couldn't find the lecture recitation recordings, but notice they are being recorded. So they just haven't been edited yet. I will do my best to get those up after today's lecture. But in general, it's just been a lot of the kind of initial setup that's been taking a lot of that time. All right, so I'd like to start by just talking through what to expect for part 2 of this first lab. And so one of the things that we're going to be talking about and that you're going to see throughout this course is an evolution of capability as realized through different robot architectures. And so we talked about these Bratenberg vehicles. And so these little things on the left here, let me get a laser pointer up. So these are Bratenberg vehicles. So these are things that just tie sensing and actuation together. So in this case, you have some kind of photoresistor, and the more light is incident on the sensor, the faster the motor it's connected to will turn. And what Valentino Bratenberg shows is that we can get some pretty complicated behavior out of something that has absolutely no cognition whatsoever, right? There's no decision-making going on, but we might still ascribe meaning and complexity to some of these behaviors. And we're going to contrast that with this drawing on the right, which is of a state machine. And so that will let us do things that are more complex. And so generally speaking, 2 types of robot architectures that you will come across are reactive. So again, sensing goes direct to action. There's no plan involved. And this is just a stimulus response. And so humans have reactive behaviors. So we can actually show through certain pain stimuli that you will react quicker than is reasonably possible for a signal to actually make it to your brain, get processed, and then send back to your muscle. And so you get these reactive responses that basically just tie your sensing to your actuation. And we contrast that with a deliberative robot architecture, which embodies the sense, plan, act process that we talked about when we were first trying to define what a robot is. Or what characterizes something that is a robot. And so deliberative architectures are much more classical robotics and also far more capable because they give us this ability to plan, right, to have conditionals. And so we're able to reason over an abstraction of the world. So to make this a little bit more concrete, this is an example of more or less reactive control. So try this newborn giraffe trying to learn how to stand up. It's not necessarily doing a whole lot of planning at this point, right? It doesn't even have a model of itself to plan with. And so we can see that this is basically just a reactive controller doing the best that it can. The adult giraffe next to it can probably execute some kind of deliberative system because it has a model for how its body works with the world, and it can plan something on top of that. So just as a bit of crowd interaction now, can anybody name an example of a robot that uses a reactive architecture that's had a fairly significant impact on society, meaning it's commercially available, it's something that you've probably seen before?
I don't know if this counts, but like the hand washing things, the automatic hand washers.
Yeah, that's a great example. So in the chat, we've got some other examples. So early Roombas, motion sensing doors, like that, those automatic doors, definitely right had an impact on society. But the Roomba is really the one that comes to mind when we think of like robotics applications. And what's really amazing is that we had no idea, sort of like the robotics community, that people would respond so strongly to Roombas. So people will anthropomorphize pretty much all things in front of them. And in particular, humans will pack bond with anything. And so when early Roombas would break, people would send them back to iRobot to get them fixed. And iRobot would say, oh, okay, well, like, thank you. We'll send you a refurbished Roomba so you can, have a functional device. And people would say, no, I want you to fix my Roomba and send it back. Right? Like people dressed Roombas up, those stretchy book covers that you may have had at one point in your life. People put those on top of their Roombas. You've almost certainly seen people putting their cats on top of Roombas, and they really like bring it into the family. So dogs would growl at Roombas, and the official guidance was that if the dog saw you scold the Roomba in front of the dog, it would kind of establish a pecking order. And so we had all these really interesting kind of social dynamic issues that this robot really like thrust into the forefront, that really just caused a lot of interesting problems. So especially later on when we're talking about, say, like bomb disposal robots, right? We don't actually always want people to have a soft spot for their robot. So soldiers would risk their lives to save these robots that maybe they had used for some period of time, might have even saved their lives at some point. And obviously that's something that we don't want to have happen. We don't want people to build these connections if it's going to risk their own lives. So this is just a quick aside. You won't find too many just purely reactive robot controllers out there that have had a big impact, but this is kind of the quintessential one. Okay, so again, simple reactive behaviors with the Bratenberg vehicle. If we have this light and that we directly connect the photoresistor to the motor, the ones that are going to get the motors that are connected to the sensors with more light are going to go faster. So we can get like avoidant behavior, we can get chasing behavior. And so we talked about this, and this is kind of where we left it with the first week of Lab 1. And in the tutorial, you implemented a reactive behavior using the ultrasonic sensors around your epoch robot. So if we want our robot to do something more complicated than this, right? So if, for example, we wanted the robot to chase after the light for 10 seconds, then I want it to get bored and just stop. I can't do that with this architecture, right? Like I need something that's going to switch me from one mode of operation where I'm chasing the light to a new mode of operation where I'm not, where I'm just stopping. And so the way that we can execute that is through state machines. So many of you have hopefully seen a diagram or a graph that looks kind of like this. For those of you who haven't, this is okay. So a state machine is a graph where each vertex represents some mode of operation or like a state of our system. And then the edges between them are the transitions, like how do we go from one state to another one? So if we look at this turnstile in the top half of the slide, it has a state called locked that it starts in. So that usually you'll have some incident arrow or like a bolded arrow coming into a state that says that that's our start state. And then in this case, that controller, right, is locked. So maybe there's some kind of electromagnet holding the turnstile in place or a physical locking mechanism on the linear actuator. And if somebody pushes on it, then it stays in the locked position. But if somebody puts a coin in here, then I transition to an unlocked state. While I'm in the unlocked state, if somebody keeps putting coins in, well, nothing is going to happen. I'll stay in that unlocked state. And then if they push, I will transition back into that locked state. So again, this is a two-state state machine for a turnstile. So if we wanted to write software to support this particular device, this would be the state machine that we're looking at. And so it's really important to think of state machines, in particular the vertices or the nodes of these state machines, as independent programs. So different controllers for your robotic system. Here's another example of a state machine to determine string acceptance. So in this case, this machine is looking to accept a string that looks that spells out the word nice, and any other input is going to cause it to go to a terminal error state. So state 6 down here, right? And so we would have our incident arrow on state 1 over here, and then our transitions are just going to be looking, at each input along the way. So we have an N, and then do we have an I? If not, we go to error, et cetera, et cetera. So we're going to design this for our robot behaviors. And one of the things that's extremely important when you are designing this is to make sure you annotate all of your edges, right? So all of the conditions that make your system transition from one controller to another. And it's extremely important that you write all of this stuff down before you just start implementing it. In robotics, programming is generally the last thing that you do. So you will want to design your system beforehand, understand how it's going to operate, what are the things that it needs in order to succeed at that operation. And only after you've gotten all of that stuff planned out do you actually go build your system. You might be able to just jump in and build a simple state machine and the associated controllers for, say, maybe lab 1 and just do all of that stuff in your head. But the complexity of these systems grows quite quickly, and eventually you will hit a point where you can't keep all of that stuff in working memory. And so it's good to get into the habit of actually designing and planning your system out. So for those of you, especially who are computer science majors, I know that this is something that tends to happen to everybody at some point in their CS-oriented career, which is you can keep your program organized in your head, but eventually in your career, hopefully this happens before you graduate, you hit something that's too large to keep in mind, like too big for you to actually implement properly just by kind of riffing it. And this is one of these things that it's just good to get in the habit of. Okay, so as I was mentioning, we want to be able to use a state machine to define multiple different behaviors or modes for our robot and the conditions that determine when you should be using each one. And the fact that we have transitions between states as opposed to a fully connected state graph means that there will be transitions your robot cannot make, and you have to be aware of when that should be the case and when that shouldn't be the case. Another thing, we're doing labs as groups, mostly to make the workload manageable and to make the debugging a little less frustrating for everybody. And if you have a state machine, or if you implement your robot using the state machine paradigm, you can parallelize much easier, right? So each one of you can take a different state and write the controller for it independently, and then come together and see if your robot is doing what you expect it to do. So here we have an example of a simple state machine for our robot. So we might start in state 1, where our controller just says to drive forward, right? Actuate both wheels, so rotate them in the right direction. And then I have a transition here that says if my front ultrasonic sensor is less than 20 centimeters, this is much better than the ultrasonic sensor on the epoch in the simulation by default. But if you get this reading, then you switch which controller you're doing. And so if we're actually implementing this, right? If we're writing code to implement this, you'll notice that in the simulator, you have a while loop, right? And so in that guard for the while loop, you're increasing time, right? You're telling the simulator, I believe the default is 16 milliseconds or somewhere in that range, let 16 milliseconds elapse, right? Simulate all the physics for that, then you run your code. And then you go back and you do that again. So you have this while loop that's running, and you'll have a variable to keep track of which state you're in. And then you'll just have a big if-else-if chain, right? So if my state is this, then I'm going to execute this controller on my robot. So that's one way that we can go ahead and do that or implement that in Python. So this is the prompt in lab 1 for part 2. You're going to write a controller that gets your epoch to do this. And so if we look at this text, there are a whole bunch of different behaviors here. And it's helpful to start pulling this paragraph apart to figure out what the individual states are going to be, right? And what the transition criteria are for operation and for moving between our states. So here's one quick pass at that. So here, the robot drives forward. That defines a controller. And then the robot continues until its sensor reads a value from one of the front distance sensors showing that it's within about 5 centimeters of the detected object. That's a transition. Right? So that's what tells you to move on to your next state. So once you're at that distance, so this other state, we're going to rotate 180 degrees in place. And so here we have an interesting transition. So if the robot's rotating 180 degrees in place and then doing something else, our transition criteria is just that we've finished our rotation. And so there are a whole bunch of ways that you could track that, that I won't, I guess, spoil here because I don't want to poison the well of creativity, but you do have multiple options for that one. Then we just find another state and so forth and so on. Do I have any questions about state machines or maybe dissecting a problem to be used in this paradigm? Okay, I'll just take that to mean that everybody is a rock star and that they will have no trouble finishing this lab. So that's great. All right, so moving on. One of the most important things in solving these like really challenging robotics problems that have lots of facets to them is being able to specify problems properly and rigorously. And so this is something that you will hopefully get a lot better at throughout this course. I would argue that this is one of the most important takeaways, even if you decide you hate robots at the end of this. Being able to rigorously define a problem gives you a much better chance of actually solving it. And like I said, programming is kind of the last thing you do when you're attacking some of these problems. So one of the inspirations I have that I'd like to kind of point towards in this regard is the statistician George Box. So George Box is super famous, did a lot of great work in statistics, but he's best known, I would say, for this particular quote, which is, all models are wrong, but some are useful. And so whenever we're trying to design a robot to do something, right? So we have that sense, plan, act formalism that we're operating within. One thing that we have to look at, right, is what are the functions of each of those pieces? So why does a robot need to sense? Well, the robot needs to sense in order to figure out what the state of the world is. And the robot needs to then plan using a model of how that world is going to evolve based on the actions that the robot takes, right? So if you can't predict the future based on your own actions, you can't come up with a plan. And then lastly, it has to be able to act in that world. And we can't necessarily guarantee that my actions are always going to turn out the way that I expected them to, right? So if I'm trying to transition the world from one state to another, maybe that's my robot is at coordinate 0, 0, and I want to move my robot to coordinate 0, 1 by actuating forward, right, on both of my wheels. I don't actually know that I'm going to be able to execute that perfectly, right? I might not end up at those precise coordinates. So the way that we address these problems, like we come up with a model of the world, we have a model of our sensors, we have a model of our actuation, but we understand that they might be noisy, that they might be somewhat misinformed, and there's a lot of cleverness involved in trying to come up with workarounds for the flaws in our model, because our models will always be imperfect. So speaking of problem specification, I'd like to go through some terminology, and first we'll work through this exercise. So I showed this in both the intro and the advanced robotics classes because I think it's a great minimum viable example for kind of being able to describe what's going on and identifying some of the things that we need to be keeping in mind when we start addressing problems. So here we have a visualization, right, of some world. And could somebody explain to me what we're looking at? Like, how do I solve this problem?
Well, it seems like you're trying to navigate the robot to the crystal. So you could look at all adjacent squares next to the robot and make sure that they are free of obstacles, and then from there plan a route in non-obstructed squares to the crystal.
Okay, great. So perfect. So we have a success criteria, right? So we want to get Wally up to like that diamond or crystal up in the top right. We probably want to avoid the case where Wally falls into the like fiery pit. Tell me something about how the robot can move through this world, like state, like how do I go from one state to another?
are we considering that this is this grid 4 connected or is it 8 connected?
That's a great question, right? And so that's even just the assumption that it's like that adjacent cells are connected, right, is something that we're bringing into this problem, right? And so the transition dynamics, right? So given that I'm in some state and I take some action and I end up in some other state, right? We're just deriving that from like how we're visualizing this problem, right? So like you're heavily biased to think that because of how I visualized it here, but that's something that we are introducing, right? And so that's sort of the lead-in for this, right? Nothing is given to us. So when we're describing a problem, you need to consider all of these things. Because if you just assume that, say, like your solver, let's say you specify a problem, you hand it to a solver and it's going to give you an answer back, it's only going to operate within the confines that you give it. So in this case, right, like we're assuming that the grid is like connected to the cells are connected to adjacent cells. So let's just say it's 4 connected. That's going to be the paradigm that we operate within. So we'll say that the robot cannot teleport. We're going to impose the restriction that it is 4 connected. Okay, and so you mentioned in order to solve this, I need to plan maybe a collision-free path up to that end state where the diamond is. In order to do that, or in order to plan, I need to have a model for how my actions impact the state, right? So what the transition dynamics look like. So if I tell the robot to go up, what happens? Well, in this case, like I would go from grid cell 1, 1 to grid cell 1, 2, but only again, if I can actually specify that that's what I expect to happen. And so here I'm building my transition model for the world. So if anybody in the audience has experience with reinforcement learning, you've done this before, right? You've had to do this. And one of the things that is really interesting with most of the generic problem-solving techniques is that they're optimization problems. And so you're trying to minimize some cost by finding, a solution that achieves that end. And if we look at, like, say, science fiction, pretty much all of the robot apocalypse scenarios come from runaway optimization problems, right? So like ill-specified optimization problems. So if you would like, this is exactly that, yep. So value iteration is a way to solve reinforcement learning problems. So yeah, so in this case, right, if we don't specify that, let's say the robot cannot go through this grid cell where there's a wall, it's going to try to do that. That's maybe an unintended consequence, but it's our fault because we didn't specify that. So this is one of the things that we have to be really cognizant of, is that specifying problems is one of the harder things to do because you have to be really meticulous with it, and we just tend to take a lot of stuff for granted. So let's agree on some common terminology to kind of use standard vocabulary as we go through this. So again, if you've taken AI, as William is showing it, telling us in chat, you've probably seen this before, but we have to agree on it. And so this is good terminology for us to adopt. So in our case, a state is just a representation of the world. Now, anything that we include in the state, or rather anything that we want to visualize in our world, we have to include in the state. So in this case, the robot's position, so our XY coordinate, that's something that we would encode in the state of the world. Now, we wouldn't necessarily put the location of the wall into our state because we can effectively encode that by putting it in our transition function. So if I don't allow my robot to transition into that state with the wall, it will never try to do that. So states are what defines the current reality of the world. And action is something that your software will do, or your robot will do, in order to transition from one state to the next. And so we can think of there being a transition function that tells us the probability of going from one state to another, given that we take some action. And so we can also formulate this a couple of different ways. So if we can just say that the transition probability of going from state S and taking action A is going to be equal to some distribution over the remaining states, but that's just a convenience thing. And we can recover that formulation from this 3-parameter version here. So we want a transition function that tells us how our world evolves, as a function of our behavior. And then lastly, we might want a reward function that tells us what's good, and what's bad. And this doesn't have to be defined everywhere, but in terms of solving this problem, one way that we can define this as an optimization problem is by saying that I might get a reward of 10 for transitioning into the state that has the diamond. And maybe I get a reward of 0 for everything else. And a reward of -10 if I transition into the state that has the fiery pit. So that's going to inform, right, what my robot behavior is. Now, what could be a problem if I have a reward of 0 for most of my state action next state transitions? What would that do? Like if we're like thinking through what our robot solver is going to do with that information. Okay, it can take a very inefficient path. And why would it take a very inefficient path? Yeah,
There's nothing.
Yeah, go ahead.
Sorry, there's nothing to tell the robot that it's getting close to its goal state.
Yeah, so if we're just running some kind of exploration on here, then we could get stuck, we can get unlucky, right? And just get stuck kind of exploring some local region here where there's no signal, right? There's nothing for us to go off of. Now, once we find a path, like our optimization-based solvers will give us more and more optimal ways of getting to our goal here, but there's no incentive to necessarily to actually be quick about this if I give a reward of 0 for all of my actions except for these terminal ones, because like heading straight to this this diamond would be effectively the same amount of reward as just kind of wandering around here for 100 million years and then going up and grabbing the diamond. So one of these tricks might be to assign a reward of -1 for all of our actions, right, as just a default, because now the longer I take, like the worse my reward is going to get. And so again, this is just an optimization formulation. We're not going to get into reinforcement learning as part of this class, but it is important to be thinking about this as like through an optimization mindset, because your search algorithms are also going to be operating under a similar regime, right? Your path planning is going to try to minimize costs, right? And so when we think about how we're defining the optimization criteria, we're really just defining a cost function. So if you have an autonomous vehicle and you tell it, you get 100 points of reward for getting me to my destination, and you get -1 for every, let's say, 10 milliseconds that goes by, your vehicle might just decide that the quickest way to get to where you're going is to drive over someone's lawn, through the fence, and like through someone else's house, because the car could survive it and the model allowed you to do that, right? So these are the things we're thinking about when we're dealing with these optimization functions. So here are 2 quick solutions to this problem. Which path is better?
I would vote that the red path is better because it's less turns.
Okay, so say again, the orange or white?
Red because there's less turns.
Okay, so that's a completely reasonable answer. Obviously, like there's not enough, right, given in terms of the problem specification to know which one of these is better. Like in terms of time steps, if I define my robot's action space as it can go up, down, left, or right, they're both the same amount of actions. But we also have some kind of notion of like safety. Like we have that kind of built into us that like this looks pretty bad. I might not even be comfortable having my robot go like that close to here. So when they were building the Roomba, they spent more money on drop sensors. So like the front wheel of the early Roombas was on like a spring, so that if it started to drive over a ledge, the wheel would fall down and it would trigger a sensor to tell a Roomba to stop. They also had infrared sensors all over this thing because their nightmare scenario was that the Roomba would fall down and hit somebody, they'd sue the company, and the company disappears, right? So we can certainly empathize with that. And so we might have this notion that, this path is safer. So we could pretend that the fire pit is an obstacle, although we're also considering this an obstacle somewhat implicitly, right? Because there's no transition that allows us to go there. So giving it a negative reward or just saying there's no way to go there could be somewhat equivalent to us. But I want to key in on something that Matthew just said in chat, which is if there's uncertainty in which way the robot is going to move or how the robot moves, then this red path or orange path is better, right? Because there's no chance that my motors are going to like go a little bit askew and then lead me there. So let's take an example, right, of uncertainty. So like orange looks like it might be more optimal. The robot doesn't have to turn quite as much. But what if I told you there's a 50% chance that there's a wall here? So now the white path is starting to look a little bit better, right? Because if we're wrong about the wall not being there, then we're gonna have to double back. And so now our path is gonna be longer. Our robot's gonna eat more battery. But also we have to consider the fact that our actuation probably isn't perfect. And so we can consider our transitions to be stochastic. So in terms of my transition function, the transition function from this state, given the action go up to this state, doesn't have to be 100%. So I could have transition dynamics that look like this. So 80% of the time, I go where I think I should be going, right? I go in the direction of the action I picked. But 20% of the time, I can either go 90 degrees counterclockwise or 90 degrees clockwise of where I intended to go. And this is a case that we're going to see a lot with even expensive robots, because there's still going to be some noise, right, in our in motor encoders that tell us, you know, where they rotated to. So now which path is better, given that there's a 50% probability up here of a wall being there? We'd have to work the math out, right? But like, there is a way to do that. We have a formalism, right, that we can use. We can use statistics to figure this out. Like, what's the expected number of steps for each of these different plans? Another question, let's say the risk of driving past the, of like hitting the fire pit, if I'm going, trying to go up from here, it's 10%, right? So 10% of the time, when I try to go up from here, I'm gonna fall in. If I say that the reward for falling in the fire pit is infinitely bad, what's the right choice of action for this state right here?
The orange path.
Yep. So okay. So the orange path would be safer. Like, avoid this possibility altogether. But even on the orange path, if I'm trying to go right, there's a 10% chance that I'll end up here anyway. That's right. So William and Josephine have keyed in on this, right? So the robot should try to go left, even though 80% of the time it's going to just like run into the wall here. 10% of the time it's still going to get to this upper cell, but there's zero risk of it falling into this fire pit, right? And so again, these are all design decisions that we have to make as we're specifying our problem. And if we specify things in a way that causes you know, these kinds of optimizations to happen, like you might imagine if you're implementing this on your robot, depending on how bad you tell it falling in this pit is or getting into this cell is, your robot's either going to just drive straight ahead like this, or it's going to start turning left into this wall. And you can imagine that you might not immediately think, oh yes, of course, if the robot is trying to ram itself into the wall, that is clearly the most safe option to go up, right? And so these are things that we have to think about as we're trying to get these autonomous systems to behave in the way that we want, while still remaining somewhat general, right? So that they're not just solving very specific cases of these problems. Okay, so this all leads up into this kind of headline of why is robotics difficult in 5 quick bullet points. So the actions that your robot takes has to be coordinated with perception and accordingly your model of the world. And that is a large task. The physical world is continuous. Other things are moving in that world besides you. And the only window you have into that world is through your sensors on board. Question in the chat, does running into the wall injure the robot? I don't know, maybe. Depends on how we formulate the problem. So for the ePuck robot running into a wall will not hurt that robot. For the race cars that you use in the advanced robotics class, if those run into the wall at full speed, they will break. And so the smarter teams put 3D printed bumpers on the fronts of those things so that when they ram into walls, the bumpers break. The smartest teams put those stretchy, retractable dog leashes on their car so that nothing breaks. But either way, right, like we have to define that for each system depending on what its action space and the dynamics look like. Making things even worse, our sensors and our actuators don't behave perfectly, right? So they exhibit noise, they are subject to lots of erroneous readings depending on how cheap your sensor is or how kind of bleeding edge the technology for it is. If we're operating with autonomous systems, we generally want to have this idea that we know what it's doing. And making something predictable, right? So providing actions that are conveying intent often requires a lot of context and comprehensive knowledge about the world. So like, obviously your robot's not going to know any of this stuff. You have to build that kind of thing in. And that's non-trivial. And then this last bit, because people exist in the world that we are throwing our robots into, it's not enough for the robots to be functional. The robots also have to be tolerable. If you make an intolerable robot, people have more than enough time and creativity to figure out ways to get rid of that robot, even if it's something that, say, the employer wants in that space. And so we have to consider usability through kind of all of these threads. Here's just a very brief overview of a bunch of different robotics research challenges. And these are all active areas of research, many of them going on here at CU in the various robotics labs in the computer science department. In this class, we'll talk about kind of the bleeding edge of robotics research challenges towards the end of the semester. But the idea here is that you're going to curate a skill set that will make this all accessible to you, right? That you'll be able to jump in to the robotics research space by the time you're done with this intro curriculum. And so in particular, the computer vision communities, the like 3D printing and like mechanical design communities, they're all kind of interrelated with the computer science side of robotics. In this class, we're going to talk mostly about navigation and a little bit about manipulation. We will use a variety of different sensors for world perception and world modeling. For your final project, you might engage in platform development, especially treating this as a constrained optimization problem, especially with respect to things like safety and cost, are definitely non-trivial. We'll learn how to read spec sheets for different sensors so that you can hop on to, say, like SparkFun, if you wanted to build something and understand basically how to figure out what to buy. In my lab, we focus a lot on human-robot interaction. So that's making robots not only functional, but safe to be around and predictable. Oral sensing, that's sound, like sonic sensing. So using like microphone arrays and things like that. Okay, so we'll come back to this towards the end of the semester, but I just wanted to throw this in at the beginning here to get thoughts moving. And if you have any questions about some of the things, or you think any one of these particular areas is especially interesting, I would encourage you to make that something part of your final projects. So here's how the rest of the semester is going to be going. Planned out. So lecture 1, we had our just overview of the course. Today, we're covering a little bit of like decision making and a little bit of locomotion. And then from there, we're going to cover forward kinematics and inverse kinematics, and I'll explain what each of those things are. And once we're done with the first 4 weeks, we essentially hit this hardware abstraction layer where we've built enough groundwork to now really treat this as more of like a planning or a high-level cognition problem. And so we'll build intelligent robots. But in order to build intelligent robots, we need to get the basic building blocks together first. And so that's going to be the low-level control and like low-level like geometric calculations that we need in order to build some of the models that we'll be using. So that was a bit of a whirlwind tour. Before I move on, do we have any questions about either the plan for the semester or any of the material that I just covered over the past, say, 20 minutes? Okay, great. So we will move on to mechanism. So we'll stay in this module for a couple of weeks. I assure you, you will have more questions as we go. So that is not a big deal. Okay, so if you go onto the Git repo for the book, I know I owe you a PDF of this on the Canvas still. This is all in chapter 2. So for future reference, when you're working on the next homework at least, that'll be something that helps. Okay, so actuation. Locomotion is the act of moving yourself, right? So if you have a robot, then locomotion is how your robot is going to get around the world. We model that by modeling the forces that are happening on each different joint and link of our robot. And so there are a whole bunch of different types of robotic locomotion. The Segway robot was a really cool one to see like a decade or so ago. Here I've got some video running of something called RoboCup. So there are a bunch of different leagues in RoboCup, from these humanoid, mini humanoid robots that have to like run around the field and actually kick the ball and get up when they fall over. There are also there's a wheeled division, and those robots are like small ground vehicles with wheel motors, so there's not a lot of balance going on, but they move so quickly that the replays actually have to get slowed down so that people can follow what's going on. Obviously, the humanoid league up at the top at the time that video was taken was pretty slow. This is a highlight reel. It's not terribly impressive to watch in real life, but they are getting a lot better at that. And this video on the bottom is the Sphero robot. And Sphero, some of you may not be aware, is a Boulder-based company. So that is our local robotic locomotion example. And then we contrast that with manipulation. So locomotion is moving yourself. Manipulation is moving other things. And you might imagine that if we can build something that can locomote over arbitrary terrain, then we can have a robot that can go anywhere. If we build a robot that can manipulate anything, then we have a universal manipulator. And if we make that the same robot, or we stack those robots on top of each other, then we have a universal mobile manipulator. So it can go anywhere and manipulate just about anything. And that's generally how we think about or think of as people as being. And that's kind of our gold standard. So we have a whole bunch of decisions to make if you're building a robot. So what is the right form of locomotion? Here's a graph showing unit power required per speed unit, right? So most of the common robotics environments are engineered to be robot friendly, and robot friendly generally means wheel friendly. So you'll have the plastic wheels, or really you won't need a suspension because it's going to be a nice polished concrete floor or something similar. And rolling is just really efficient. Here you can see railway wheel has by far the greatest power efficiency here. Walking, or especially running, not super efficient, takes a lot of energy. And so this is one of the reasons why you haven't really seen too many successful examples of quadrupedal or bipedal robots out there. And so now we're kind of seeing that, wait a minute, most in the environments that we're starting to get interested in are not super robot friendly. So now we need different circumstances. And something that's quite interesting is that there are no examples of wheel structures in nature at macro scales. So that's kind of just an interesting trivia bit. So in terms of actuators, right, things that can affect our locomotion, pretty much everything is an electric motor. That at least certainly what we'll be using. And electric motors look like these things, if you have not seen one before. And they have a little spindle that turns. So you apply current and it turns. You apply more current, it turns faster. And so usually, if you have a brushless DC motor, direct current motor, it's going to have high RPM. So the spindle is going to go really fast, but it's not producing very much torque. So if you were to, for example, glue or Loctite something onto that motor and you applied some resistance to it, your motor is probably going to burn out, or it's more likely to burn out because it's got low torque available to it. The way we get around that is through gearing. Lecture 2 quiz, do not worry about that yet. That is something that we may get to if there's time, and if not, I'm not worried about it. So in general, there may be quizzes during this lecture. None of them are graded, so it's just a comprehension check. And so those are on the Canvas, but I'm more interested in actually making sure we get through the material than I am going through that that comprehension. No, it's a great question. I appreciate you bringing it up. Okay, so most of the motors are going to be these brushless DC motors. We can put an encoder on them. So this is a device that you're going to place, let's see, somewhere like tracking what the rotation is at. So that way you can tell how much your motor has turned. And so we use that to determine position or just how much rotation has happened since we've applied our current. Then we contrast that with a stepper motor. And so a stepper motor has a fixed number of steps. So it's not continuously rotating. And so it has a given number of positions that it can be in. And as we apply our current, it'll just go through more like click through those positions essentially. Less common, they're linear actuators. Depending on how big your robot is, you might need pneumatic or hydraulic actuation, but we won't really be dealing with any of those in this class. So when we're building our robot, we're deciding which robot we're going to use. We also need to have a notion of stability. So static stability is what we would call something that is able to just stand up without any input or effort from us, right? So this thing could be unpowered, and if it doesn't fall over, we would call it statically stable. And so in this case, certainly the robot on the left might be considered statically stable, right? So if there's no power, this thing's probably not going to fall over. This robot here, the inverted pendulum, that's going to fall over, right? Unless it's very perfectly balanced, and which we can probably assume it's not going to be. And so we would say that this inverted pendulum robot exhibits dynamic stability, which means that it can use movement to stay up. And so bipedal robots tend to be dynamically stable, right? Because they're able to rebalance themselves if they're not, say, like perfectly their center of mass isn't perfectly over the middle point of the legs. But we can also have robots that encompass both of these ideas, right? Like where there is a configuration where it's statically stable, but also when it's moving, right, there are configurations where it's going to fall over or it's going to crash. And we would call that hybrid stability. And so like a four-legged static pose, we might consider to be statically stable. But in order for this like four-legged robot to move, it needs to put itself in a position where it's not stable anymore, right? It's basically falling forward or falling into its next position. And as I've been mentioning, the Boston Dynamics Spot robot is a great example of stability, right? So in the background, we can see some statically stable positions. But in order for the Spot robot to actually walk, right, and locomote, it needs to take itself off balance. Now, in order to actually make this kind of safe for the robot to do, it's not going too far off balance, right? And so when that random person just kicks the robot, depending on how much incident force there is, like the robot may or may not be able to recover. And so if you want a robot that's able to balance itself on dynamic terrain or icy terrain or something like this, you probably don't want to have it too far outside the realm of stability at any given point, because that's going to limit its ability to recover. The thing that was spinning on that robot is actually a laser sensor. Yes, so that is a LiDAR unit. So the thing it's basically just lasers coming out, and it's spinning as fast as it can here so that you can get a 360-degree picture. And we will talk about LiDAR, and we will actually use LiDAR in, I believe it is lab 3 or 4, to do some mapping work. Okay. So theme for today has been precise specification matters, right? And like planning is helpful for us to actually make progress on stuff. So with that in mind, our robot's going to need a model of the world, right? Because we're going to have to use that as the basis for figuring out what we're going to be doing. And that's going to require some notion of self, right? It's like, where am I right now? That tends to be the most popular one because that's going to be common across all of your robotics problems. But also you have to consider others, right? So like the objects that you're trying to pick up, or the soccer ball you're trying to kick, or the goal you're trying to kick it into. And so first question here would be, how do we precisely specify location and pose, right? Like we need to be able to encode everything into a model, like a computational model for our autonomous systems to use. So how do we precisely specify where stuff is in the world?
coordinates and stuff.
Great, pick
Triangles.
some coordinates. All of these are correct answers, but they're not the full answer. So let's say I have this can of Diet Coke. How do I know where it is? What do I need to describe this?
You need a point of reference.
Okay, so we talk about coordinates. So I need a point of, let's say the point of reference is my webcam. So I've got my object, got a webcam. How do I specify where this thing is relative to like
Using a vector that goes from your webcam to the can.
Okay, so what's in that vector?
Just an X, Y, and Z coordinate, and also you would need the dimensions of the can and so like where the vector points, probably like the center point of the can.
Okay, so great start. So X, Y, and Z coordinate, right? So I need a frame of reference. We'll assume, generally speaking, that the frame of reference is a point on the robot that we pick. So in this case, we'll just say that the robot is my webcam that's looking at me right now that you can see. So that'll be my origin point. And so I can derive XYZ coordinate, right, for this object. Is that all I need? So you mentioned that I might need the dimensions of the can, but I could also just pick a point, maybe like in the middle or the center of the can, and just call that my reference point. What else might I need to actually like define where this is? So like, if I wanted one of you to hold up a can in your webcam in the exact same pose as I am, what would you need?
I was thinking of integrating this into the geometry part, but I guess if your geometry is separate, then you need rotation as well.
Okay, tell me about rotations.
So just like how much it's rotated in the pitch, yaw, that stuff.
Yes.
So 6 coordinates in total.
Okay, so I have 6 coordinates, right? So X, Y, Z, roll, pitch, and yaw. And so I'm seeing in the chat like direct discussions of like velocities and accelerations, and we can get that from time series of those 6 dimensions, right? The X, Y, Z, roll, pitch, yaw. So if you have that 6-dimensional vector, right, that uniquely, or that's going to define, right, like where our object is in the world, like how it's oriented relative to me. Great question. What is roll, pitch, and yaw? So here is a figure. So roll is going to be tilting the wings, right? And so these are just rotations around each of our axes, X, Y, and Z. So if we want to specify where an object is, right, we need 6 degrees of freedom. And so we're going to call these environmental degrees of freedom. Now, if I'm in a 2D environment, right, so our epoch robot just rolls around on a plane, right? Now, we can consider elevation and whatnot, but let's just say for now, like in the rectangle arena that you used in the tutorial, that's a 2D plane. So what are the degrees of freedom that we have to consider for that one?
Maybe there's no pitch and no Z.
Yeah, so we can, I mean, like we could use all 6 degrees of freedom because it's simulating in a 3D world, but we can reduce the set. So depending on, like we need X and Y, and we need 1 rotation axis, right? To like model like which direction the robot's going to be facing at any given moment. So we can come up with like we call that a projection, right? Or a subset of those dimensions. So we have 3 position variables and 3 orientation variables. And this 6-DOF pose is something that's going to come up a lot. And so again, the idea here is that we want to fully characterize the state of the plane. Now, can anyone think of a case where I might need more than just this like 6 degree of freedom, like single point to define, okay, multi-part things? Tell me more about multi-part things. What about those multi-part things might be, okay, if the size is dynamic?
Basically, if there's any other characteristics, you need more numbers.
Right. So what exactly. And what we're describing here is essentially if my object is rigid, then I only need the 6 degrees of freedom, right? Because like I can pick any point on here and that point's not going anywhere. But if I have something that's like stretchy or deformable, now I have a different situation, right? Like that one point no longer tells me the full story. And so let's see what. So that's good. The plane that each rotational axis exists, that's going to be dependent on which coordinate system we use. So Weebots in particular uses like a fairly strange choice for which axis is which and where they're pointing. But we will get into that once we go to the odometry lab next week. But that's a good question, right? That's a good thing to think about, which is how are we defining our coordinate systems? And so again, that's a choice that we're going to have to be making. So let's talk quickly about just what do we mean by a rigid body, right, or a rigid object. So here, I'm going to say that we are going to define, so this variable O, so it's going to be a three-dimensional vector of real numbers. And so these are O is going to represent all of the points that make up my object. So if I were to like explode this robot into like an infinite number of like infinitesimally small points, all of those are going to be in this set O. And so what I can say is that for any pair of points on my robot here, I want to make sure that at the end, at any time step, right? So at any point in this object's future, the distance between those points is the same as the distance that I started at. So in other words, if I pick these 2 points, P and Q, and I measured the distance here, then I ran my simulator, right, for T time steps. At the end of that, P and Q will be the same distance apart. And that I can do that for any 2 points on here, or rather every 2 points on here. And so another way to think about this is through like transformations. And so if I'm going to transform my rigid body from like one spot to another spot, then I have some characteristics that I also need to take into account. So for example, length between our points is going to be preserved, and the angle between the axes that I would define at those points is also preserved. And so we can represent that through these 2 equations of length and cross product. You don't really have to memorize this or write this down. This is just something to help you conceptualize what we're talking about. And like we can leverage this, but the important thing is to like put formalism first, so that when we talk about this stuff, we can at least point back to the foundation that gives us the justification for saying it. Okay. So we're going to talk a little bit more about degrees of freedom, just because this is somewhat confusing because it's an overloaded term. We use the term degrees of freedom to refer to 2 different things at different times. And so when we're talking about our robotic degrees of freedom or mechanical degrees of freedom, we're really talking about the number of controllable points of actuation. So does the robot need a model of its physical body stored somewhere in its memory? Generally speaking, yes. If you want your robot to plan through the world, it's very likely that it's going to need to know, say, in this case, like where its joints are, how they're configured, and what its link lengths are. Because if we don't have that, it's going to be really hard for us to, say, figure out if we're about to collide with something, say, for a given configuration of joints. So that tends to be something that you do when you've created a robot. In Weebots, you'll also notice that there's separate fields for appearance and collision models. And so one of those is going to be used for planning, and the other one is just kind of for our benefit, right, to look at. So mechanical degrees of freedom is the number of controllable degrees of actuation. Now, most robot arms, so most manipulators, have 6 degrees of freedom in the environment space, right? So that means that they can move their end effector in XYZ, roll, pitch, and yaw, right? So I can have my environmental degrees of freedom, right, which are the variables that define pose. So again, 6 degrees of freedom. But I can also talk about mechanical degrees of freedom, which are my points of actuation. So if I have 6 joints, I would say I have 6 mechanical degrees of freedom. So can anybody explain why it might be really nice to have 6 environmental degrees of freedom at the robot's end effector? Like what might that afford me the luxury of doing? Manipulation. Sure. But yeah, go ahead.
It allows you to get the robot manipulator into weird spaces.
Exactly, right? I can yeah, I can do any, like that would let me move the robot end effector kind of more freely right throughout the space. So it'll be easier for me to get it to a configuration that I want it to be in. So degrees of freedom in Cartesian space or other environment space, put another way, is a little bit tricky, right? Because that's not directly controllable. Usually I can't tell my robot like, okay, move the hand straight down like along the y-axis by 5 centimeters, right? Because that's going to require a whole bunch of complicated joint movement, right, to achieve that end effect. So I'm controlling my motors or robot through motors in the joints. And so when we talk about mechanical degrees of freedom, we're talking about joint space. So another thing that we would consider, right, is that we might want to have more mechanical degrees of freedom than there are environment degrees of freedom, right? So if my environment degrees of freedom is 6, so XYZ roll pitch yaw, I might want to have more than 6 joints on my robot. Why would I want that?
In case something breaks.
Okay, so yeah, so that, I mean, that kind of redundancy could be great. Put another way, right? How many mechanical degrees of freedom does a human arm have? Like a typical human arm have? So if we think of a mechanical degree of freedom as basically just having a motor, right? So you have like the spindle that can spin along, like it can rotate along an axis, right? So like as an example, our elbow, right, has 1 mechanical degree of freedom, right? Because so it can just bend. How many do I have in my shoulder? How many axes can I rotate around with my shoulder? 3. How many axes can I rotate around with my wrist? Yeah, so you can get 3. Like you can get a little bit of roll like on your wrist without moving the rest of your arm, right? So in that case, right, I have 3, 1, 3. So I sum those up. My arm has 7 degrees of freedom. And the reason why that's interesting, right, is we can look at this in terms of variables and unknowns, right? So we can set up a system of equations. So if I have 6 degrees of freedom, right, in the space that in my environment, so XYZ roll pitch yaw, and I have 6 motors in my robot, and they're configured in such a way to not be, you know, redundant or overlapping with each other, then I have 6 equations and 6 unknowns. So I will have a solution, right, for any given space, right, or configuration that I want. But if I go for 7 degrees of freedom, right, so now I have 7 equations and 6 unknowns. And so I might have multiple solutions for a given end effector position, right? So if you pick a position where you want your hand to be, because we have 7 degrees of freedom, there are many solutions, right, for your joint angles to get there. The answer is a little bit complicated to Andrew's question in the chat because it just depends on how the joints are configured, but pretty much yes, right? So like 6 degrees of freedom, we can, in our simplified model, we can assume that suggests that there's a unique configuration of joints for each target 6 DOF pose. So with only 6 DOF, you have to worry about singularity. So these are positions where the robot arm might get like stuck essentially. And sure, absolutely. You still have to be concerned about that with more degrees of freedom, but you especially have to be concerned about that as your degrees of freedom, your mechanical degrees of freedom reduce. Okay, so this terminology is really important to internalize. And so when we talk about things like Cartesian space or operational space or task space, we're talking about the environment, right? So that's the XYZ roll pitch yaw degrees of freedom. Otherwise, when we're talking about mechanical degrees of freedom, we're talking about how many joints or points of actuation that we have for the robot. Okay, so now let's talk about our epoch. So how many mechanical degrees of freedom does the epoch have? And what are they? So we were talking about mechanical and not environmental. And so, yeah, so there's one for each wheel. Like, so what can I actuate, right? Like, put another way, like which joints can I ask control of, right? Using the, like, say, get motor or get device. So I have 1 degree of freedom for each wheel. How many environmental degrees of freedom does the epoch have on the 2D plane? And somebody already answered this one. So we have 3, right? So X, Y, and yaw, assuming that the X, Y are the planar coordinate axes. Okay, so we call the epoch a differential drive robot just because its 2 wheels are independently actuated. And so given the stuff that we've been talking about today, why might it be hard for epoch to drive in a straight line? So each wheel is controlled by a motor. And why is it hard to get both wheels to do the same thing? Yeah, these are all great answers, right? So, and all of these can be correct. So there could be motor noise, right? So the motors aren't absolutely identical. And so same current might have different internal friction, et cetera. Manufacturing differences in the wheels themselves, especially like the epoch robot is one that you can cut out of acrylic. So depending on how you do that, you might run into some trouble. Somebody mentioned that there are 3 wheels on the epoch. One of them is actually not actuated at all. It's just sitting there. So that we wouldn't consider that a mechanical degree of freedom. But that's a good observation. And so, yeah, we're just gonna have different motors. So we're gonna have different rotations. We're gonna have different radii of the wheels themselves. But obviously, we're not gonna just stop there. So how can we mitigate that difficulty? What are we gonna do?
You can use the encoders.
Okay, so encoders, what are encoders gonna tell me about this?
So you could use encoders to calculate the distance each motor has traveled, and if one motor has traveled less or is like traveling at a slower speed, then speed it up.
Absolutely, right? So essentially, I can use sensors to kind of assist me, right, to overcome this kind of imprecision. And so even if my model is wrong, right, like I'm going to assume perfect everything because I'm not going to be able to characterize maybe the noise offhand. But as long as I also accept that like there is imprecision in my transition model, well, I can use feedback from my sensors to kind of try to correct that kind of stuff. So that's exactly right. And that is something that we will be doing through this course. So next we'll talk about some control paradigms. So essentially different ways to control our motors, our actuators. So this is a video from ICRA 2015. So ICRA is one of the major robotics conferences. And so this is, the title doesn't really matter at all, but it's a great demonstration of different types of control strategy. And so we'll have, oops, get rid of the laser pointer before it will let me play. Okay, so we can make difficult tasks easier by making clever decisions, right? That's a recurring theme in the class. So let's say we want this robot arm to polish this table. So we have a couple of options. If we use position control, then we need to tell the robot essentially where each point on that table is that we want it to move through. And that could be tough. That's certainly not going to be flexible, right? If we move that table at all, it no longer works. What they're showing here are different types of control. So force control is a mode where the robot just calculates what the joint changes should be to impart a consistent force along a particular vector. So if you're polishing, maybe you want that force vector to be mostly diagonal in like a way that creates progress. And so here they're using the controller from their research paper that's using a blend of force control and impedance control, which is essentially just a way of establishing like a control paradigm that uses some ratio of force output versus motion input. So there's a relationship between force and position, velocity, and acceleration that makes this a little bit more stable than just force control by itself. And so here, when you have a dynamic object, they didn't have to model that at all, right? They didn't have to come up with a strategy that takes into account the fact that this thing is going to move, right? Because they were clever with their control paradigm choice. And then torque control is just measuring or establishing a consistent amount of torque at a particular joint or over a collection of your joints. And so in our class here, we're going to be mostly focusing on position and velocity control. So particularly for spinning the wheels, we actually don't care about the position too much. Like, we're not going to set the wheel positions. We're going to set the velocity that the wheels are turning. And then we're going to calculate position based off of that. Okay, we've got a couple of minutes left, so we'll just end by going through a couple more examples just to solidify the concept here. So how many mechanical degrees of freedom does a bicycle have? And what are they? So remember, this is the points of actuation. So the things that you can rotate essentially, or like, like the control surfaces that you can use.
My guess is it's 2.
What are those 2?
Forward and backwards, and then turning the front wheel.
Yep. So we're seeing it in the chat as well. So the handlebars and the pedals, right? So you can steer with the handlebars and you can pedal. And so those are your mechanical degrees of freedom, right? Those are the actuation interfaces or control surfaces that you have. And then how many degrees of freedom does a bicycle have in the environment that we're using it in? So what's the operational space of that?
3.
And what are they?
Forward, like going forwards and backs.
Okay, so like, let's say x-axis is going out of the bike.
Yeah, there's roll and then there's yaw.
Yeah, and also, so that can be correct, but also the folks in the chat saying 6, that is also a correct answer, right? So you can hop the bike if you are talented enough. You can pitch and roll the bike if you are good or bad enough at it. And so this is one of those more open-ended responses, right? So like, it kind of depends how you use it. And so that's like also similar to how we're doing the epoch stuff. Some of you may have noticed that you could impart arbitrary like impulse forces on epoch in the simulator and cause it to go flying. So again, we just have to kind of figure out for our model, what are the relevant degrees of freedom that we want to actually model, and like which ones are worth considering, which ones are not. So with that, we will end here with just another demonstration of manipulator degrees of freedom. So these are mechanical. So we don't just have a single rigid body here, right? So the point, I can pick a pair of points that might change over time. And so here we have a 1 degree of freedom manipulator. This one has 2. This one has 3 because the gripper. And then this one has 4. And so this gets increasingly complicated. I actually have a robot next to me right now. So let's see. Let me turn off my virtual background. That might be harder or easier said than